Hi, good evening, good morning, good afternoon, and to every good whatever time namin ito panoorin. So, this video lecture will be on evaluating ISRs and for our microcontrollers segment na ating EEE153. So, ayun, if you find yourself yung kayong magbabarkada, nagko-compare kayo ng ISR, uy, mas maganda yung sa akin, pre. Mas maganda yung ISR ko. Pero, paano mo ma-defend na mas maganda yung sa'yo? So, usually, we look at a few metrics when we talk about ISRs. So, yung coverage natin would be on yung main metric natin, which is interrupt latency. And then, titignan natin yung ISR overhead at saka CPU percentage. And then, lastly, titignan tayo ng mga techniques para mabawasan natin yung latency or overhead ng ating interrupts. So, interrupt latency, if familiar kayo sa term na latency, it usually means some sort of time or delay. So, interrupt latency is the time since the occurrence of the interrupt event until the interrupt is serviced. So, for example, meron tayong push button. Kapindot mo ng push button, gaano katagal bago mag-respond si microcontroller. So that will be a concrete example of interrupt latency. So we usually split it into two parts. So the first part is from the occurrence of the actual event to before the start of the interrupt service routine. So medyo nasa hardware na to, yung mga delays ng transmission ng signals within the microcontroller and yung how often our CPU would check for interrupts. So, medyo as a programmer, wala kang masyadong magagawa doon. May limitations na ito ng hardware. So, what we usually focus is yung second part, which is the number of instruction cycles used by the ISR, also known as the ISR overhead. So, depende sa resource na titingnan mo, these two combined, yung interrupt latency, meron din naman mga sources na kino-consider na hiwalay si ISR overhead sa latency, which is just yung first part. So, for the purposes of EEE153, we consider the contribution of both when we talk about interrupt latency. So, moving forward, ang ISR overhead is just the total number of instructions for the interrupt service routine. So, that includes yung I-entry, I-body, and I-exit. So, si I-entry, as the name suggests, pagpasok mo ng ISR, which includes yung prologue instructions or what we can also call yung context save. So, yung di ba, pag pumapasok ka ng kahit anong function naman or ng subroutine, meron tayong context save na ginagawa sa simula, yun nag-store tayo sa stack ng mga register values and nag-move na stack pointer. So yun yung sa I-entry. Yung kapartner naman no, yung I-exit, yung epilogue or yung context restore. So yung pagtanggal from the stack and pagbalik sa mga registers. And of course, yung I-body, which is actually may control lang tayo as programmers. So kung gaano kadami yung instructions na nilagay mo sa loob mo ISR definition mo. But usually, yung total number of instructions, well, it tells something, pero there's more to that, and that is the ISR CPU percentage, which multiplies yung IISR to the frequency ng ISR. So pag multiply mo yung number of instructions times yung frequency, yun makukuha mo yung average number of instructions per second na dinedevote for the ISR. And then pag dinivide mo siya sa clock cycles per second, makukuha mo yung percentage ng CPU time na ginagamit for an ISR. So alternatively, pwede natin hiwalay yung ISR natin over our instruction frequency is actually yung ISR execution time. So yung total time it takes to execute the ISR. And pag multiply natin siya dun sa frequency ng ISR times 100, makukuha natin yung percentage ng CPU time. So, ano ibig sabihin ng CPU time? So, for example, meron akong CPU time na 10%. Ibig sabihin yung CPU natin, 10% of the time, ISR yung ine-execute niya. So, 1 time out of 10 times, pag chinek mo yung CPU, nag-handle siya ng ISR. So, ano yung makukuha natin dyan? So, if we have a higher instruction count, tataas yung execution time natin and tataas din yung latency. Of course, obviously, pag mas mahaba yung service routine, mas matagal tayo mag-service. And then, another thing is, pag mataas yung CPU percentage, we are using more time on ISRs. So, we have less time for the more important stuff. So, remember na yung interrupts natin parang mga segue lang yan. So, siguro real life example, siguro nag-aaral ka. And every so often, nauuhaw ka. Gusto mo uminom ng tubig. So, tatayo ka muna, kuha ka ng water, and iinom ka. So, parang interrupt na siya in a way, yung pag-inom mo ng tubig, and yung regular program flow mo is yung pag-aaral. So, ayun, ang pag-inom ng tubig, importante siya, hindi mo siya pwedeng iwasan. Pero hindi mo rin pwedeng gawin yung kada 5 minutes iinom ka ng tubig. Pwede pa yun. Siguro every minute, wag uminom ka ng tubig. So parang mga 20 seconds ka kumuha ng tubig. So 40 seconds na lang yung pwede mong ilagay sa pag-aaral tapos iinom ka na ng tubig ulit. So parang masyado kang madaming time na dine-devote sa hindi mo naman may goal. So, another example siguro, if meron kang microcontroller na nagko-control ng smart farm, siguro yung pag-monitor niya ng mga water levels, mga humidity, temperature, syempre kailangan regular siya nag-check. Pero for example, user ka, may kailangan input, gagawa yun ng interrupt sa microcontroller. And if you take too long to service the interrupt ng input, baka ma-miss mo yung mawala yung pag-regulate mo and baka may masamang mangyari. So, ayun. So, we would always want a lower CPU percentage. Pero that doesn't necessarily mean a high interrupt latency or a high interrupt instruction count. So, dalawa yung factors na tinitingnan natin sa CPU percentage, which is yung total number of instructions at saka yung frequency ng interrupts. So, we can have a low instruction count, pero pag parating nangyayari yung ating interrupt, ganun din. Malaki pa rin yung overhead or malaki pa rin yung kinakain niya sa CPU natin. So, both those things ang tinitingnan natin when we consider yung CPU percentage. So, kaya dito sa baba, we want both a low latency and a low overhead or yung CPU percentage. So, okay, so let's have an example here. So create a code wherein each positive input will toggle the output bit kay port B. So ang key thing dito is, ayun, may mechanical switch tayo na may bounce time na 5 milliseconds. So, looking at a sample code, siguro ganito yung tsura niya. Yung interrupt enable natin, yung interrupt flags, turn on and off na lang natin during the course of the ISR. Then, meron tayong delay dito. And then, mga if statements. So, if nag-1 si port A, wait lang tayo ng the bounce time. And na-check natin kung 1 pa rin siya. And if 1 pa rin siya, ito-toggle natin si port B. For PIC32MX, so you should check your datasheet kung iba yung device mo. Yung I-entry natin for this example is around 19 instructions. And then yung sa exit naman is nasa 40 instructions. So what's left is yung dito sa gitna. So let's have one instruction here, one instruction for here, tapos one instruction din yung pag-check. So, yun yung +3. And then, meron tayong delay na, ayan, di pa tayo sure. And then, +3 pa ulit for the check here and yung sa pag-change ng port and yung pag-clear na flag. So, yung return statement, hindi na siya nakasama doon. And ayun, so medyo more or less eyeball lang naman to. Yung number of instructions. Usually, if meron mga work problems on this, given naman na siya. So, ayun, so to get yung instruction count ng delay, ayun, assume yung system clock na 60 MHz. Yung kailangan natin na instructions for the delay is 60 MHz times 5 milliseconds, which is 300,000. So yung ISR natin, actually, yun na siya majority. Nasa 300,000 clock cycles siya. So medyo malaki in this case. So what can we do to, so kung 300,000 clock cycles, ano kaya yung CPU percentage niya? Okay. Complete ng bilis. 300,000 over 60 megahertz. Ayun, actually, let's say nangyayari siya once per second. So, meron tayong 0.5% na CPU percentage. So, medyo malaki. So, one way to reduce this is to use semaphores. So, a semaphore is a global variable that acts as a flag. So, yung flag, ang semaphore actually, ang meaning niya is just a fancy term for a flag that acts to signal something. So, usually, ang real-life semaphores yata ginagamit sa mga airport, yung mga nagpa-flag. And then, using semaphores, ang ginagawa lang ng ISR is mag-set ng flag. And then si main code yung gagawa ng actual na work. So how does that look like? So kanina, yung ating ISR, meron pa siyang delay, meron pa siyang check ulit. So sa ISR natin, we just set a global variable, port A pressed, to be true. And then yung ating main code, ang gagawin niya lang is, ayun, if si semaphore is nag-true, siya yung gagawa ng delay and siya yung mag-check and magre-re-enable ng interrupts. So in this, for this example, ang actual ISR natin is just this 1, 2, 3, 4, 5 lines over here. And ayun, yung iBody natin, 4 commands lang siya. If hindi, ang return statement kasi is equivalent sa iExit. Ayun, 63 na lang yung ISR. So, comparing this dun sa original na 300,000, it's a significant improvement if you ask me. So, another way to reduce yung ating latency is yung paggamit ng tinatawag na shadow registers. So, in a microcontroller, lalo na dun sa mga mas recent or mas high performance, meron tayong dedicated set of registers para dun sa current na context. So, parang sinashadow niya yung current laman ng registers para pag pumasok tayo sa ating ISR, wala na masyadong gagalawin dun sa mga registers na yon. So, since naka-shadow naman na, so normally kasi, di ba, meron kang register set and isi-save mo muna sa stack and then tsaka mo pa lang siya magsa-start. So, ang gagawin nun, meron kang register set tapos may naka-shadow sa kanya. And yung naka-shadow, automatic na siyang hindi mo nalalagay sa stack yung register values mo. Nasa shadow register na siya. So, mag-run lang to, tapos babalik na siya doon. So, ganun siya nakakatipid ng time or ng instructions. So, ang nababawasan niya na instructions is for the prologue and epilogue. And then, ayun, so sa XC32 or sa PIC32MX, pag nag-MP lab ka, usually ang lalagay mo dito, pag software context, software restore and save, context save and restore, ito ang SRS paggagamit ng shadow register set. So typically, ayun, nasa 2 to 3 instructions less kahit wala kang gamitin masyadong registers. Pero nagsiscale to if dumami yung temporary variables mo. Kasi if konti lang naman yung mga registers na gagamitin, konti lang din yung matitipid mo sa paggamit ng shadow registers. So, yung kanina, kung ito yung example natin, soft yung gamit niya, ito ay SRS, hindi hard. Ayun, so mababawasan lang si IN3. So in 17 siya or 19 minus 2. Si I exit is 40 minus 3. So 58. Comparing that to 63. So medyo maliit lang. Pero for example, madalas nangyayari yung interrupt na to, it will still mean something. And especially if lumalaki na yung mga ISRs mo, lumalaki rin yung effect ng paggamit ng shadow registers. So usually doon sila ginagamit. So ayun. And then the last thing you can do to reduce yung latency is to program in assembly. So pagka kasi nag-compiler tayo, it might take unnecessary steps. Baka pag yung mag-context save siya, meron siyang mga sinisave na hindi naman kailangan i-save. So you as a kayang mag-program in assembly, pwede mo siyang gamitin to reduce the latency. So, ayun. Paano ba ito? So, for example, pwede kang magtabi ng special or nung section ng registers mo for interrupts. Tapos yung, so what if lahat ng mga S hindi mo gagamitin sa interrupts, puro mga T registers na yung gagamitin mo sa interrupts, pwede naman yun kung magawa mo siya. So, pwede mong bawasan yung number of instructions mo. So parang ito yung default pag diretso sa compiler. Pero, ayun, pwede mo siyang i-streamline na ito na lang yung gamitin. So, actually, that's it. In summary, yun, main topic natin is yung interrupt latency. So, it's a rough evaluation of how good you service an interrupt. So, mas mabilis na pag-service, of course, mas mabilis na service, mas maganda. And then, as programmers, we usually focus yung sa ISR overhead at saka ISR CPU percentage kasi yung delay from the interrupt to the ISR, wala na masyado magagawa about it. And ayun, ang CPU percentage takes into account yung ISR overhead and yung frequency ng interrupt itself. So, two factors ang kino-consider natin when we try to reduce yung CPU percentage. Then lastly, meron tayong mga software tweaks such as Semaphores at saka hardware tweaks such as shadow registers that can allow us to improve or reduce yung ating ISR overhead, which will eventually lead to lower CPU percentage and lower latency. So that's it for this video. I think the next video will feature some examples or some sample problems involving interrupt latency. So that's all for today. Thank you very much.